Hello students, I welcome you all to my channel Engineers Academy. Do hit the subscribe button if you haven't done it yet. Now let's solve this problem which says that determine the components of the reaction at the ball and socket joint at A and the tension in the supporting cables DB and DC. So here we have at A the ball and socket joint. So the ball and socket joint can provide the reactions along all the three axes. So we will have AX reaction, we will have AY reaction, and we will have AZ reaction. So we are required to find AX, AY and AZ. And here on for this 3-meter length of this beam or this assembly, we have this load distribution. This is 800 Newton per meter. So the load is distributed over this 3 meters length. So the resultant of this distributed load will be 800 multiplied by 3. So that will be the area of this distributed load. So 800 multiplied by this 800 multiplied by 3. So that will give us 2400, and that 2400 resultant will be acting at the center of this distributed load area. So that will be acting at somewhere here, that is from this distance will be 3 divided by 2, that is 1.5 from this particular end. So let me show that resultant of the distributed load that is going to act somewhere here, and that will be 2400. This 800 multiplied by 3 is 2400, and this end is the resultant is at a distance of 3 divided by 2, which is 1.5 meters. Now since in the problem statement it said that we are required to find these AX, AY and AZ and the tension in both of these ropes. So for that we have to cut these ropes. So let me cut this rope somewhere here, and we will have the, so let's say that the tension in this DB cable is, let's say, T1, and let's say that here this is T1, this is T2. Now in order to solve this problem, first of all we have to find this T1 and T2 as a Cartesian vectors. So first of all I will write T1 Cartesian vector. This will be equal to T1 magnitude times the unit vector from D to B, since T1 is acting from D to B. So T1 times the unit vector, or T1 and the dot product with the unit vector. So we can say that this is T1, and then the unit vector is the position vector from D to B divided by the magnitude of that position vector. So this is T1, and now we have to find the position vector from D to B. So to find the position vector, we need to travel from D along the X, Y and Z to reach that point B from this point D. So from D we need to travel this 1 meter distance in the negative X. So that means that 1 meters in the negative I. So I will write 1 meters in the negative I. So we will reach here, and then from here we need to travel this distance. So this distance is in the positive Z, and this distance is 3 minus this 1. So this distance is 2. So we need to travel 2 meters distance in the positive K. So I will write plus 2K. So when we travel this distance and then this distance, then we need to travel 1.5 meters in the negative J, that is in the negative Y. This is the positive Y, so we need to travel this distance. So we need to travel 1.5 in the negative J, so minus 1.5 J. And then we have to find the magnitude of this position vector. So the magnitude will be 1 square plus 1.5 square plus 2 square under the square root. So this will give us 1 square plus 1.5 square plus 2 square. And if we look into this 2.692 as a fraction, so this is square root 29 divided by 2. So this is approximately equal to square root 29 divided by 2. So now T1 Cartesian vector, this is equal to T1, and we need to divide each of these components by this. So 1 divided by square root 29 divided by 2. So 1 divided by square root 29 divided by 2. So that will be 2 divided by square root 29. So this is minus 1 divided by that. So minus 2 divided by square root 29I and then this minus 1.5 divided by this, so that will be 2 multiplied by 1.5, so that will be minus 3 divided by square root 29j, and then we have 2 divided by this, so that will become 4 divided by plus 4 divided by square root 29k. And now if we multiply this t1 with each component, so we will have 2t1, this is 3t1, and this is 4t1. So this is the Cartesian vector representation of that t1, and this is the magnitude of the x component of t1, the magnitude of the y component, and this is the magnitude of the z components. And the negative sign tells us that the x component of t1 is in the negative x. Similarly, the y component, the x component is in the negative x like this, the y component is in the negative, and the z component is in the positive k. Similarly, we have to write this t2 as a Cartesian vector. So for t2, I will write again t2, and then t2 will be equal to t2 times the unit vector. This is t2 magnitude, and the unit vector is from d to c. So this is equal to t2, and again the unit vector from d to c is the position vector from d to c divided by the magnitude of that position vector, and this is t2. So again we will have that same position vector, but instead of minus 1.5 we will have plus 1.5, since this point C is at a distance of 1.5 in the positive y. So everything will remain the same, only this minus 1.5 will become positive. So in order to find the position vector from D to C, we need to travel 1 meters in the negative I, 2 meters in the positive k, and 1.5 meters in the positive j. So we will have minus 1I plus 1.5j plus 2k. And again, if we find the magnitude of all of this, so we will have that same square root 29 divided by 2, since in finding the magnitude, the negative signs have no effect since we take the squares. So the magnitude of this will be square root 29 divided by 2. And similarly, if we divide all of these, so here we have minus, here we have minus sign, and in this particular case we will have plus, and the remaining components will remain the same. So we can write that t2 is minus 2t2 divided by square root 29 I. This will become plus 3t2 divided by square root 29j plus 4t2 divided by square root 29k. So this is the Cartesian vector representation of that t2. So now if I apply the summation of forces along x, the summation of forces along x, that must be equals to 0. So first of all, let me represent the components of t1. So t1 have one component in the negative x. So t1 has one component in the negative x. So this is in the negative x. Similarly, t1 will have one component in the negative y, and it will have one component in the positive z. So this one is t1x, this one is t1y, and this one is t1z. Similarly, let me show the components of that t2. So again, t2 will have one component, the same component in the negative I. So this is t2, this is t2x. Similarly, this is in the positive j. So we will have one component like this. This is t2 y, this is the y component, and we will have one component in the positive k. So this blue one is t2z. Let me write that this is t2z. Let's say that this is t2z. Before going to apply the summation of forces along x, I am going to apply the summation of moment about the x-axis, that will be equals to 0, and I am going to apply the scalar approach for this problem. Since the scalar approach for this problem is more appropriate, since this problem will be very easily solved if we find the moments by using the scalar equation that moment is equal to f times d. So we will apply the summation of moment about the x-axis, this is equal to 0. I am going to apply the summation of moment about the x-axis since majority of the forces or components are passing through that x-axis, and their moment arm from the x-axis are 0, so they are not going to produce the moment about the x-axis. So this 2400 Newton, the resultant is passing through that x-axis, so it's not going to produce the moment about the x-axis. Similarly, this T1Z and T2Z, both the components, they are passing through that z-axis, so they are not going to produce the moment about the z-axis. And these x components, this T2 and T1x, they are parallel to the x-axis, so they are not going to produce the moment about the x-axis. And AX, AY and AZ, they are also intersecting, passing through the x-axis, so they are not going to produce the moment about the x-axis. So only the y components, this T1y and T2y, they are going to produce the moment about the x-axis. So now if we look into this T1y, this T1y is going to produce the moment about the y-axis in about the x-axis in this direction. So if we curl our right hand fingers in this direction, so the thumb will point out in the positive x. So this means that T1y is producing the counterclockwise moment. So you will write plus T1y, and the perpendicular distance of this T1y from that x-axis is 1 meters. So this is the perpendicular distance of this T1y from the x-axis. So 1 meter is the moment arm of T1y. So I will multiply this with 1. And similarly, this T2y is going to produce the moment about the x-axis in this direction. And if we curl our right hand fingers in this direction, so the thumb will point out in the negative x. So this means that T2y is producing the clockwise moment about the x-axis. So I will write minus T2y, and again the moment arm of this T2y from the x-axis is 1 meter. So we will multiply this with 1. So this is equal to 0. And from this we can say that T1y is equal to T2y. And we know that T1y is this. The magnitude of T1y is 3 T1 divided by square root 29. And the magnitude of T2y is this 3 T2 divided by square root 29. So now this will cancel out, so we will be left with T1 equals to T2 equals to T. So this means that the tension in both the cables is the same and they are equal, right? And as we can see that this whole assembly is symmetrical about the YZ plane, and these point C and point D, the distance of point C and point D from the Z axis or from the XY plane are symmetrical. So that is why T1 is equal to T2. So T1 is equal to T2 is equal to T. Now after the summation of moment about x-axis, we are going to apply the summation of moment about the y-axis. So that will be equal to 0 as well. So the summation of moment about the y-axis, that is equal to 0. So now again this AY, AX and AZ, they are intersecting with the y-axis, so they will not come into our equation. Similarly, this T1Z and T2Z, they are similarly this T1y and T2y, they are parallel with the y-axis. They are not going to produce the moment about the y-axis. So these x components and these z components are going to produce the moment about the y-axis, and this 2400 is going to produce the moment about the y-axis. So now as we can see that this T2x, so it's going to produce the moment about the y-axis in this direction. And if we curl our right hand fingers in this direction, so the thumb will point out in the negative y. So this means that T2x and T1x both are producing the clockwise moment about the y-axis, since we have the thumb in the negative y. So I will write that minus T1x, and the perpendicular distance of T1x from the y-axis is 1 meters. So that is the moment arm. So we'll multiply it by 1. Similarly, T2x minus T2x into 1. And again this T1z, this T1x, T1z and T2z, they are going to produce the moment about y-axis in the clockwise direction as well. So we will write minus T1z, and again the perpendicular distance of this T1z and T2z from the y-axis is 1 meters. So we will multiply this T1z with 1, and similarly minus T2z into 1, and then this 2400, this resultant is going to produce the counterclockwise moment about the y-axis is if we curl our right hand fingers in this direction, so the thumb will point out in the positive y. So we will have plus 2400, and the perpendicular distance of this 2400 from that y-axis is 1 plus 1.5 plus this 1.5. So this 1 plus 1.5 plus 1.5, so this is 3 4. So we will multiply this with 4, and this is equal to 0. So now since t2 is equal to t1 is equal to t2, so from this we can say that this will become minus 2tx, or we can say that this will be minus 2t1x. We can add up both of these since t1 and t2 are equal, and similarly t1 and t2 are equal, so we can say that this is minus 2t1z. And if I bring this term to the other side of equation, so this will become minus, and if we multiply both sides of equation by minus sign, so everything will become positive. So we will have plus 2t1x plus 2t1z equals to 2400 divided by 4. And similarly we can divide this whole equation by 2. So if we divide both equation by 2, so we will have t1x plus t1z equals to 2400 into 4. So this will be 2400 into 2, so that will be 4800. So 2400 into 2, that is 4800. So now t1x magnitude is this. So we can write that this is a 2t1 divided by square root 29, and t1z magnitude is 4t1 divided by square root 29. So plus 4t1 divided by square root 29 equals to 4800. So now we can add up both of these. So this will become 6t1 divided by square root 29 equals to 4800, and from this we can say that t1 is 4800 into square root 29 divided by 6. 4800 multiplied by square root 29 divided by 6, this gives us 4308. T1 is equal to 4308.13 newtons. So now if I apply the summation of forces along the x-axis, that will be equals to 0. So the summation of forces along x, so now as we can see that this t1x plus t2x, so we can write that t1x plus t2x. So t2x is also equal to t1x since t1 and t2 are equal. So let me write t2x. Then we have that ax, and this t1x and t2x, they are acting in the negative x, so we will write minus, and here we will have minus. So minus t1x minus t2x, and ax is acting in the positive x, so plus ax. So this will be equal to 0. So from this we can say that ax is equal to t1x plus t2x, or from this we can say that this is 2t1x since t1 and t2 are equal. So ax is equal to 2 times t1x. T1x magnitude is 2t1 divided by square root 29, and t1 magnitude is now known. This is t1 magnitude, so we can replace this t1. So this will be multiplied by 4308.13. So this is 2 into 2 is 4 multiplied by 4308.13 divided by square root 29. This gives me 3200 approximately. So ax is equal to 3200 newtons. Similarly, if we add up all the forces along y, and the summation of forces along y, that must be equals to 0. So now along y we have this ay and this t2y minus t1y. So we will have ay plus t2y minus t1y, this is equal to 0. So since T1 and T2 are equal, so y components are equal but acting in the negative direction, so this means that they will cancel out each other, so Ay equals to 0. Similarly, the summation of forces along the z-axis is that must be equals to 0. So now along the z we have Az, this Az, so plus Az, then we have T1z and T2z in the positive z, so plus T1z plus T2z, and then minus that 2400 Newton. This resulted, this is 2400 Newton, so minus, and this is equal to 0. Since T1 is equal to T2, so we will have 2 T1z. So we can say that Az is equal to 2400 minus 2 T1z. So 2400 and T1z magnitude is 4 T1 divided by square root 29. So 4 T1 magnitude is known, 4308.13 divided by square root 29. So this is equal to 2400 minus 2 into 4 multiplied by 4308.13 divided by square root 29. So Az is equal to 4000 approximately, and we got minus sign. Az is equal to 4000 Newton. So the minus sign tells that the actual direction of Az is in the downward direction. The assumed direction is not accurate. Az magnitude is 4000 and it is acting in the downward direction. So now we have determined T1 equals to T2, and the magnitude of this T1 equal to T2 is 4308.13. X is equal to 3200, Ay is equal to 0, and Az is equal to 4000 Newton, and it is acting in the downward direction. So this is the solution of this particular problem. I hope it will help you in your learning. Let me know in the comments if it helps in your learning. Like my videos and subscribe Engineers Academy for such more problem solutions.